Okay, so let's have a look at the answer. So this one, you had HCl in there. So you should immediately look at HCl and know it's an acid. Okay, we're going to give you very obvious things. You know, there are acids that you may look at and not know it's an acid, but HCl, you know, hydrochloric acid is one of those classics. You know, sulfuric acid, nitric acid. If you don't immediately look at HCl and think it's an acid, then you need to do a little bit more work on your general basic chemistry, because you need to be able to just look at these things and know, okay, HCl is an acid. You know, sodium hydroxide is a base. So we've got an acid present, okay? So we're going to follow the acid catalyzed reaction. So if we look at the acid catalyzed reaction, what we say there is, you know, the oxygen is going to get protonated to form a more reactive carbonyl group. So we take the electrons that we have here and we protonate. Okay, so we've activated our carbonyl group. We've got this strong positively charged oxygen, which ultimately means we've got a very electron deficient carbon. And then we're going to take our methanol. So methanol isn't a source of OH, because that methanol is CH3OH. So the carbon-oxygen bond is going to be quite a stable one. It's going to be more stable than the oxygen-hydrogen bond. So methanol isn't a source of OH minus, it's a source of MEO. But it's not being deprotonated here, so it is an uncharged nucleophile. But what we have is a lone pair of electrons on the oxygen that we can use as our nucleophile. So these can react with the carbonyl carbon. Therefore, the carbonyl carbon have too many bonds, so we need to break a bond. So we're going to break the carbon-oxygen double bond. That has the added advantage of neutralizing that positive charge. And we've added our methanol to our carbonyl group. And then the final step is we need to deprotonate it. It's charged at the moment, but we're under acidic conditions, so we know that there will be protons in solution would be quite happy because we're in an acidic environment. So we can say that the electrons from here can be used to neutralize that. And we end up with our hemiacetal product. So if you're not sure about what's happened there, this is what I mean. You have to start looking at the different kind of reagents that we're showing you and begin to understand what they are. So looking at MEOH is methanol, knowing that methanol is an alcohol. If you see ETOH, that's ethanol, and I'm sure lots of you know that ethanol is an alcohol. Okay? So what you need to do is be able to look at these things and understand HCl is an acid, sulfuric acid is an acid, nitric acid is an acid. The name gives it away, okay? But you have to know the chemical formula for those ones as well. And we kind of assume that you would know those because they're the kind of things that you would have covered for hopefully years before you've come here. You would have seen them in GCSE, you would have seen them in A-level, you would have seen them in BTEC, access courses, foundation courses, whatever you've done before. These are things you should have come across. So, the last kind of thing we're just going to look at is what's called acetal formation. So we've done a hemiacetal, but there is something that's called an acetal. And what that is we know that the alcohol can react with a carbonyl, okay, and we create this hemiacetal, but under acidic conditions, a further reaction can occur if you have excess alcohol in the system. And again, I'm sure lots of you would have had excess alcohol in the system. That's why you didn't turn up for 9 o'clock, I'm guessing. Okay, so this is the hemiacetal. Okay, this is the one that we've created before. And I said to you that the reversible reaction required you, under acidic conditions, to protonate, yeah? So for the reversible hemiacetal, we protonated the OR group, didn't we? But I did say at the time, of course, there's a choice here. We could protonate the OH group, but that doesn't get us back to the reverse reaction, so we weren't going to do that. But now, we know it can happen, so let's see what would happen if we actually protonated the OH group instead. So, we'll use a lone pair of electrons here, and we form a new bond. Okay, and so we've produced this protonated OH group. And hopefully, some of you are looking at that going, I kind of recognise that molecule. I mean, it's attached to something else, but H2O is water. And we know that water is an incredibly stable molecule. It's far more stable than you think it should be, because if it wasn't, we wouldn't be here, because we would have all evaporated. So we know that water going as a leaving group must be very good because it's going to be stable. So the OH group by itself is quite difficult to make leave unless you've got these basic conditions. But if you protonate something to produce H2O and H2O plus, that's a really powerful leaving group. So if it's a really powerful leaving group, then can we use that to our advantage? Is there any way we can make that leave the reaction? And the answer is yes, we can. Because now, if we form a carbonyl, okay, the carbonyl carbon is going to have too many bonds, so therefore we need to break something. And we've set up now a really powerful leaving group. So that can leave as water. So what we end up with now is a carbonyl with a positive charge and water. Now, when you look at that, what do you see? Well, you see the activated carbonyls that we've been doing before. I mean, admittedly, normally we've protonated them. It's not an R group, it's a H. But if you look right back at the very first thing we were doing, we had it as just E. We had it as something attached to that oxygen that meant the oxygen had a positive charge. So this is just another form of that activated carbonyl. So if we've got an activated carbonyl and we have a weak nucleophile, well, we know that those two things can react, can't we? Now, if the water reacts back, we just go back to where we started from, not particularly useful, but we know in our system we have another alcohol molecule. So, if we take our ROH, we can do the same reaction that we did on the previous slide, or the previous example, where we can use the lone pair of the oxygen as our nucleophile, attack the carbonyl carbon. We then have to break the carbon-oxygen double bonds. That has that advantage of neutralising that positive charge again. We add our alcohol, just like we did in the previous example. And then finally, we can deprotonate it. And what we now have is a carbon that has got two OR groups attached to it. When we had one OR group, it was a hemiacetal. Now we have two OR groups, it's an acetal. So you might look at it and go, there's a lot of curly arrows there, a lot of mechanistic stuff, but actually look at it in detail. None of the things that I've just done now are any different to some of the stuff we did earlier. They're all following that general mechanism. They're either trying to create something that's charged, so a charged activated carbonyl, and then you can have your uncharged nucleophile attack, or you're creating a charged nucleophile that will attack your unactivated carbonyl. So they're following the same things. It's just realising that once you've created one product, so the hemiacetal, looking at it and saying, okay, if this was to exist in this environment that we've put it in for the reaction, and there's an acid available, could that acid react further? And we know it can because we can send it back in the reverse direction. But what about if we decided to take a different path? So instead of protonating the OR group that we just added, we protonate the OH group that's there. And what we'll start seeing when we look at the more complicated, or what I call more complex carbonyl groups, where you've got things like amides, you've got oxygens, but you've also got nitrogens. And so you can have a difference in protonation of those. So that's forming the acetal group. And again, all of that is reversible. We're not going to do the reversible reaction now because it's just the same as the hemiacetal one that we've already done. So the final thing for today is, the protonation of the hydroxyl group. Sorry. What I should just point out is that you have to be able to protonate that hydroxyl group for it to work. So therefore, this can't be done under basic conditions. Because under basic conditions, you won't protonate the OH group. So it has to be under acidic conditions. So the final thing is just to think about, we've done it with oxygen, okay, but sulfur can do the same reactions, okay? And in fact, sulfur is slightly more nucleophilic than oxygen. And that's, again, we're not going to discuss it in too much detail, but it's to do with that sulfur is a bigger atom, which means that the electrons in the outer shell, the ones that we're using to do the reaction, are further away from the nucleus of the atom. So they aren't as attracted to the nucleus of the atom, which means that they can go out and do other things much more readily. So just to show you an example, if you take your simple aldehyde and instead of our OH we use our SH, that can do exactly the same reaction mechanism. What that is effectively a S. The S has a lone pair of electrons. We wouldn't do it against this, we'd have this, we would have protonated this already. Okay, but the sulfur can act in exactly the same way as the oxygen. So all of those reactions that we've just looked at, instead of, if you see it with our SH rather than OH, you can follow exactly the same mechanisms. Okay, so it's not different, the mechanistic stuff is exactly the same, it's just you can do it with sulfur instead of oxygen. And you would have a hemithioacetal and you would have a thioacetal. Okay, so that's just a kind of a, if you see examples, and again, when you start looking at drugs, you see some that will have thiols in them. If we think back to, there is a thiol in one of the amino acid structures. So this kind of reaction can occur within protein active sites, for example, because you have a thiol there. You also have ones where you have OH groups there. So, after this, what you need to be able to do is make sure that you can demonstrate the reaction between the aldehydes and ketones with oxygen and with sulfur, okay?